各位同学们听得到声音吗？Hello，好，谢谢。同学可以看到画面吗？
可以。
OK，谢谢。然后在右边的对话框帮我签名，谢谢。Okay, time's up. So last time we getting at the confidence interval. Hold on, let me change the point. Okay, confidence interval. In order to provide a point estimate, sometimes it is not that trustworthy. So an interval estimate between two statistics that include the true value of the parameter with some probability. This is called confidence interval. Like there's a lower bound L and upper bound U are provided, and there's a significance level alpha. So it's called the 1 minus 100 minus 1 minus alpha confidence interval for the unknown mean mu.
教授，您现在没有声音。
老师，你好像关掉麦克风了。
OK， 现在有声音了吗？现在有没有声音 ？Hello？
有了。
Sorry. I should go. Sorry. I should share. 好，现在可以听得见了吧？啊 ，OK。So there's an important thing. Let me go over again. So the confidence interval, that is interval estimate for that unknown parameter between two bound. There's two bound, lower bound and upper bound. Denoted by L and U, and this is unknown parameter mu in between. So that is called the 100 times the 1 minus alpha confidence interval. So for the unknown parameter, so the 1 minus alpha is called the confidence coefficient. Typically, alpha is between sometimes we use a 1%, 5%, or 10%. So the half length mu u minus mu or mu minus L is called the accuracy of the confidence interval, called half length. So interpretation confidence interval, if the really large number of such intervals are generated, it's resulting from a random sampling, then 100 times the 1 minus alpha of this interval will contain the true value of the mean. For example, if we generate 100 of this interval, if alpha equal to 5%, that is called a 95% confidence interval for mu, 95%. If we generate 100, at least 95 out of 100 intervals will contain the true value of mu. So actually, we still don't know the real location of mu is. So confidence interval have a frequency interpretation. However, confidence intervals do not have a probability interpretation. Is that clear? So the confidence interval, okay, let me say it again. This must be in the test. If you do not understand, please let me know. Let me say it again. Must be in the test. Let me rephrase again. If we generate 100 intervals like this, if alpha equal to 5%, so that means at least 95 out of 100 intervals will contain the true value of mu. However, we still don't know where exactly the real value of mu is. Actually, we don't know. So the confidence interval have a frequency interpretation. However, confidence interval do not have a probability interpretation. Is that clear? Do you have any question? So this must be in the test. All right. Okay, so then there's a
Excuse me, Professor.
Yes, please.
There a student, she says she cannot log in.
Who?
As the student from Hong Kong. And,
From Hong Kong. How come?
yeah.
I don't know. I already provide. Hold on. How can I help her? How can I help her? The student from Hong Kong. How can I? She cannot log in. She cannot log in. How come?
老师他说他好像有什么提出一些什么要求，可能进入这个 Teams 的团队。
他的，等一下我看一下，我来教他看看。Hold on。到底要怎么弄啊？这是头痛。我看一下啊。好，那个他有，好，来等一下，我来把他加进来看看他的学号，新增成员，来，他的学号知道吗？会不会帮我问一下？
我等一下，我找一下。
把学号贴给我试试看。董静，他的学号
对，
董静怡啊。
对，他是
好，
我说我打一下，我打在留言区。
没有，你打在 LINE 上面好了，好不好？我直接贴好了。来，我看一下。我看一下，董事长的静是哪个静？哦，我看到了，董静怡111A1G 是不是啊？
对。
OK，来，我加他。哎，加不进来，我不知道为什么发生错误。我看一下学生董，我没有办法加他啊。董静怡，我这里也加不进来啊。伤脑筋。我看要怎么加。那他行不行用访客？就是我给他的连接行不行进来？行不行跟他联系一下，看看用老师提供的连接，他看行不行进来。
老师他说你给的那个连接是加入团队的连接，不是说影片连接。
好，等一下哦，等一下，看要该怎么办。那我现在连接，等一下，设置会议连接，沟通。会议记录在一起，请及时开始。这时候我也不知道该怎么办。 全荧幕效果计时，会议选项，因为我们只要用 Google Meet， 它不允许我们录影，所以说就不能了。是。试试看这个，看看这个7D。对啊，这个啦。我刚刚又贴了一个链接，让他看他行不行，就是应该是我们今天会议的链接。
老师有，他说他进来了。
OK， 好，好吧，那我们回到正常。OK， 可以了哈。Okay, so I hope everybody gets in here. So count the interval in equation 2.24 might be more properly called two-sided count interval, as is specify both a lower bound and upper bound on mu. So sometimes in quality control application, the one-sided is also applicable, might be more appropriate like this. So the one-sided lower bound at least are greater than some constant interval lower bound. So that is chosen. The probability that L less the greater than or equal to mu is equal to 1 minus alpha. The other type is called the one-sided upper bound. This is mu greater than equal to L, the 1 minus alpha. So it could be either way, the mu greater than or equal to L, or the mu less than or equal to U. So this is two different cases. So count the interval on the mean with variance unknown. So this is let me say that. Let me do that again. Let me do that again. Let me do it again. So this is a mu. So when there's an unknown variance sigma right here, then we use Z. Let me say it again. If the sigma unknown, okay, known, that actually is the sigma is known, and Z should be used. Then the Z alpha over 2 going to the percentage point of the standard normal. Let me say it again. As long as the sigma is known, and then the standard normal should be used. Sample distribution is the standard normal distribution. Then there's a two-sided, there's a one-sided, there's a one-sided, right? Okay. So reconsider the computer example. For example, if the sample mean the 79.25 millisecond, we know that the reasonable point estimate for the mean response time is about 79.25. To find the 95% two-sided. So in which case, we assume this is A. since the sigma is known beforehand. Sample size of 25. And the 1.96 since actually alpha equal to 5%, 95% in here. The alpha is equal to the 0.05. Okay, 0.05. So you can check the z-score equal to the 1.96. Why we use the z? Since the sigma is assumed to be a known standard deviation. So in the original example 4.1, the alternative hypothesis one-sided. So in this situation, some analysts prefer to calculate the one-sided counter interval. So in which case, Minitab for the example 4.1. And the textbook also provide a 95% lower bound mu. That is compute from that is upper. This lower bound is 76.62. So notice that in the counter interval from Minitab does not include 75. Furthermore, so hypothesis equal to 75, so need to be rejected since the 75 is not included. So this is not an coincidence. So in general, tests significant for parameter at level significance will lead to a rejection hypothesis if and only if parameter is not included in the counter interval. So null hypothesis and the counter interval are parallel each other. Once is a counter interval does not include that value, null hypothesis is going to be rejected. If the counter interval included and null hypothesis will not be rejected. P-value. So traditional way to report the results of hypothesis testing. To state that a null hypothesis was or was not rejected as a specified alpha level or not. Yeah, let me say that. So it is often called a fixed significance level test. Let me put example. If mu equals 75 was rejected at the alpha equal to 0.05 level of significance, that is to say, if the p-value is less than 5%, then we reject it. If the p-value is greater than alpha, then we do not reject the null hypothesis. This statement conclusion is often sometimes misleading because it gives the analyst no idea about whether the computed value of test statistic was just barely in the rejection region or not. So we would like to use the p-value approach. How close, how significant of that test statistic is. So it has been adopted widely in practice. The p-value is a probability that test statistic will have a probability value that is at least as extreme as the observed value of the statistic when the null hypothesis is true. So it is important, this statement. So it is a value at least as extreme as the observed value of statistic when the null hypothesis is true. Under the assumption the null hypothesis is true, the p-value is at least extreme of the observed value is, then the p-value conveys much information about the weight of evidence against H0, and so a decision maker can draw a conclusion at any specified level of significance. So even though if our p-value is equal to the point, for example, 0.06, for example. The p-value equal 0.06. Alpha equal to 0.05. It is greater than that. Conventionally, we do not reject the null hypothesis. However, we know p-value is really close to alpha. So in some special consideration, we might reject the null hypothesis since this value is too close to the alpha. So it depends. So that leads to decision maker, the personal discussion. So it is so the decision maker can draw a conclusion at any specified level. The alpha, it depends on the decision maker. So which level he or she would like to make the decision making. So then we move to the p-value calculation. The p-value is the smallest value. The smallest level of significance that will lead to rejection of the null hypothesis value, p-value, the smallest level. Then for the normal distribution test discussed previously, it is relatively easy to compute the p-value if sampling distribution of these is used. Z known is computed value of the test statistic, then the p-value. This is two-sided. Equal, not equal. So this two-sided. Then for two-sided, the p-value like this. So if the test statistic, is right here, we calculate the right tail times 2. Why? Since it is two-sided. If this mu equal to the mu null, alternative hypothesis mu greater than mu null, So in which case we only calculate one-sided. If it is in the null hypothesis is greater, so we're going to calculate. If the z null is right here, we calculate the upper probability. That is the p-value. Once while the alternative hypothesis is greater. On the contrary, if the null hypothesis is less than mu null, then and this is a z null right here. Then we calculate the lower probability. This is the lower side, the lower tail. Why? Since the alternative hypothesis is lower. So this is the 5 z null. Then it's kind of yeah, I keep using that. Okay. So the 5z is the standard normal cumulative distribution function. So it must be check. Actually, which is also defined in chapter 3 to illustrate this. So consider the computer response time as well. And this is two-sided 2.66. This in this case is greater than that. So this is 1 minus 5, 2.66 about the 0.0039. This is about 0.4%. So thus the null hypothesis will be rejected as at any level of significance alpha is greater than or equal to 0.00939. As long as the extreme, the level of significance level is set up greater than p 0.00939, this example, and the null hypothesis equal to 75 will be rejected. So if the null hypothesis would be rejected, alpha equal 1%, but will not be rejected if alpha is only 0.001. This is 0.1%. So, however, 0.1% is a seldom use. Typically, alpha we use 1%, typically 5%, or 10%. Like this. In this case, only 0.1%. We would not reject it, however, which is rarely used in practice. So likewise, suppose that x is normal random variable with unknown mu and unknown variances. So we wish to test the null hypothesis. So that means that equal to the standard mu null. So in this case, the sigma is unknown. This is unknown mu and the unknown sigma squared. So know that this problem is similar to that of the section. So in which case, as sigma is unknown, it might be estimated by s squared. It's replaced by s. If s is used, and the t sampling distribution should be used instead of the z. Okay. The reference distribution. So the reference distribution for this test statistic is a t distribution with a degree of freedom of n-1, remember. Degree of freedom n-1. Where does it come from? Because of this. When the sample variance is used, the degree of freedom comply with the sample variance. This is n-1. That's where the degree of freedom come from. So for a fixed significance level test, the null hypothesis will be rejected if the absolute value of the test statistic is greater than the the critical region T alpha over 2 n-1. So T alpha over 2 n-1 denote the upper alpha over 2 percentile point of the sampling distribution T, corresponding to the degree of freedom n-1. The critical region for the one-sided likewise, if the alternative is greater than, if the test statistic is greater than this alpha, this upper score. If the alternative is less than, so the test statistic is less than negative T alpha. So this is pretty similar to the case we discussed in the standard normal distribution. So 1 minute, please read the example, 1 minute. Read the example 4.2, 1 minute. So I'll be back in a minute. Okay, back to the slide. Rubber can be added to the asphalt to reduce the road noise. When the material is used as a pavement. So table 4.1 shows the standardized viscosity called CP of 15 specimens of the asphalt paving material. The total you have a 15. The stability viscosity. To be suitable for intended pavement application, the means the stabilized viscosity should be equal to 32. 32 will be the best viscosity suited for pavement material. So test this hypothesis when alpha equal to 5%. Based on experience, we are willing to initially assume the stabilized viscosity is normally distributed. We assume this is normally distributed. So in this case, then based upon the computation of the 15 specimen, we have the sample mean equal to the, it's about how much? 3,210.73. Then we take the sample standard deviation about the 117.61. So in the midterm examination, so everybody should prepare your own calculator. In the examination, the computer is not allowed. The pad is not allowed. The only allowed is the calculator, electronic calculator, and the textbook, and the older book. All the different textbooks are allowed. So we can test the test statistics. There's a 0.35. So this value is so small. So we almost can conclude the mu equal to the 3,200 cannot be rejected. Cannot be rejected. So since the calculate value of the test statistic does not exceed since let me ask you, this is a two-sided test or one-sided test? Gentlemen, Miss Zhao, Zhao Xiaojie, could you answer my question? It is a two-sided. Okay. It is two-sided or one-sided? You do not pay attention to my class. What do you say?
我说双尾 two side。
为什么要想那么久？
我在找我的麦克风。
Okay, sure. Then, okay, this is two-sided test. Then, t since the alpha equal 5%, they're two-sided. So one-sided should be the 0.025. The y degree of freedom is equal to 14. 来，那个圣诞树，你回答为什么自由度是14 ？Why? Y degree of freedom is equal to 14.
因为要减1。
Okay, 15. Good. The 15 minus 1. That's why we need the degree of freedom equal 2.145. Thank you. Very good. So this 2.145 or is it greater than 2.145 or less than minus 2.145, we will reject it. However, you can see that the t value 0.35. 0.35 is between the critical region, so we do not reject the null hypothesis. So there's no strong evidence to conclude the mean stabilized viscosity is different from the 3,200 CP. So the assumption of the normality for the t-test can be checked by constructing a normal probability plot of the stabilized viscosity data. So we plot this. What is your impression when you look at the probability plot? Does it deviate from the normal distribution? Yang Ting, what is your impression about the normal probability plot? Yang Ting. Hello.
喂，
说话啊。
就是它会是一个很直的线，然后 data 会在那个直线的周围散布，几乎是正向。
Okay, thank you, Yang Ting. And then, since almost a point, almost fall on the straight line, this is no particular doubt. The data will not follow the normal distribution. So we can conclude that the data are drawn from a normal distribution, since most of the point almost fall on the straight line. So look at the mini tab, the computer printout right here. So this is the two-sided, mu equal to 3,200 versus mu not equal to. So this is the two-sided test. Then the n, this is the mean, this is the standard deviation. 117.6 is come from here. 117.61. So this standard error mean the mean of standard error. This standard. This is the X bar. How can we calculate that? This is the S divided by square root of n. Can you get this number for me? S is 117.6. Take the square root of 15. Yeah, let me do the calculation. You also can check it is, so in the examination, I will ask this kind of question. 117.6 divided by 7. Okay. Yeah, there's a 30.36. In my calculation, I get the 30.36. Would you get the same answer? Would you? Does everybody get the same answer? Where does this come from? Where does this come from? Bandai. Do you know where does this number come from? Banzang. Please explain. Where does 30.4 come from? 30.4怎么来的？ Where does this number come from?
听到 by version， 然后除以4。
除以多少？ No, it is absolutely wrong. The boy from the computer science department, can you answer my question? Are you here? Are you there? Hello? Hello? I assume he's not here. The lady, the lady from Vietnam. Hello. Hello. Who is willing to answer my question?
Excuse me, Professor.
Yes. Could you answer where does this number come from?
This is equal to standard deviation divided by square n.
What is n?
It is the error mean.
In this case, what is n? What is the
n is equal to 15.
15?
Yes.
Okay, pay attention to the class. Then this is the t, so the 0.35. This is a 0.35. The p-value, could you explain the p-value? Let me, okay, then. Yang Ting, could you explain? In this case, p equal to 0.729. What is your conclusion?
P 大于它的 alpha 的话，就会 fail to reject H no.
Okay, thanks. Thank you. Hold on. In the p-value is so large. The 70 the almost 73%, and much greater than the alpha. Alpha typically use 5%. So in such a case, as long as the significant level is greater than 0.729, and then we will reject. However, which is not possible, so we do not reject the null hypothesis. So p-value for the t-test. So the table for the standard normal can give the exact p-value. T has a selection. So the heading of the table, so which should be use extrapolation or intrapolation, unless the value test t-set match the value. So you need to do some calculation. So p-value can also be obtained by Minitab. Use a probability distribution to function calculation value. So count interval on the mean of a normal distribution with a variance is unknown. Variance is unknown, like this. It is unknown, S should be replaced, should be used. This is one side. This is the upper, this is the lower bound, and this is the upper bound. Okay, then reconsider the stabilized viscosity data from the example. So this is a confidence interval between the 3,145.59 and the 3,275.87. On the other way, this is upper bound. This is upper bound. If you only so we like to use upper bound in case 95%. 95%. So then we move to the next one, to inference on the variance of the normal distribution. So hypothesis testing, we now review the hypothesis testing on variance of the normal distribution. whereas the tests on the mean are relatively insensitive to the normal assumption. So test procedure on the mean are not normal assumption. However, test procedure for variance are not. This is quite sensitive. So so suppose that we wish to test the hypothesis that the variance of normal distribution equal to a constant like this. Sigma square equal to sigma known square. On the contrary, which is not equal, then this, the n-1 times, since the sigma is unknown, so which need to be replaced by the s squared. So n-1 divided by s squared. No. n-1 times the sample variance divided by the sigma known square, which is this null value in the null hypothesis, will follow the chi-square distribution. So as long as the chi-square distribution like this is always non-negative. So this is the lower critical region, this is upper critical region. So we will calculate this. Then for a fixed significance level of test, the null hypothesis rejected is greater than the upper critical region, or if the less than lower critical region, we also reject it. So if it is a degree of freedom is corresponding to the n-1 as well, since it's corresponding to the s squared. So if the one-sided alternative is like it is less than particular value, so if the test statistic is less than the chi-square test score, 1 minus alpha, this is lower. Alpha, 1 minus alpha, n minus 1. For the other one-sided is greater than the value, so need to be greater than the chi-square alpha, since this is the probability on the right tail is alpha with a degree of freedom n minus 1. So this is a one-sided test. So to illustrate this procedure, now we take a break. Okay, back to the slide. Testing procedure.没有看到画面吗？同学，没有。Hello，
有啊有啊，
是看到投影片的画面吗？还是
没有现
没有看到？
在是
等一
现在
下哦，
是那个你的 file 的。
哦，等一下，我来把它可能跑掉了。等一下，我再来一次。等一下，等一下。OK，这样应该有了，谢谢。这样有了哈，同学。
有。
OK, thanks. Okay, then to illustrate this procedure, consider stabilized viscosity data. So that is equal to 100. The greater than 100 square. Standard deviation equal to 100. This is sigma naught. I would like to use like this. This is equal. So then, can you tell me this is a one-sided test or two-sided test? 洪一凯
One side.
One side, good, since they're greater than, right? So value of the test is computed from that equation, so we stuck in. In this case, the n equal to 15, so -1 is 14, times the standard rate, the 117.716 square, and sigma square, the sigma known square, this is a null value. This is a null value. The sigma 0 square, this is a null value. Null value. So finally we get the 19.36. So we check from the appendix, the upper 5% value of the chi-square with 14 degree of freedom, 23.65. So 19.36, still smaller than the critical value. Since the compute value of the test statistic. So 洪同学，你认为在这种情况 under such a circumstance, we reject or we do not reject the null hypothesis. Mr. Hong.
我觉得应该是 accept.
What do you say? Accept. Good. Okay. So we cannot reject the null hypothesis. Yeah, very good. So this is a mini tab, computer output. And standard deviation 118 is around here, right here, right here, okay, from here. Then lower bound, the lower bound is for standard deviation. The lower bound is A176. So chi-square is 90.737, p-value about this, since alpha typically equal to the 0.05. So for this p-value, so as can be seen, this is 15%, the 5%. This is much greater than, so we do not have enough evidence to reject the null hypothesis. So lower bound for the variance is like this. It's greater than 100 the square. So this is a lower bound for that. The lower bound for standard deviation. This is lower bound for the variance. So you can see that this should be the 1000. In which case this is no, this is 10,000. This is only 8,000. 8,176. So in such a case, we do not reject the null hypothesis. Okay. So for the confidence interval, this is a little bit complicated for normal distribution. So in between the sigma square and divide by is a score. This is upper 1 minus alpha. So this is up. The lower score, this is the upper score. So this is two-sided confidence interval. So this is a one-sided confidence interval. So I truly believe they have been emphasized in the elementary statistics course. I just give it. And then inference about the population proportion. The inference on the population proportion, that mean. So this is the P naught. Actually is equal to the X divided by N. So suppose I wish to test the null hypothesis, the proportion P is a percentage. What is the proportion or the fractional proportion of population equal to standard value? See the P naught. The test we will describe is based on the normal approximation to the binomial distribution. So X follow the binomial distribution. So in such a case, so we're going to do the there is a binomial justification. So X plus 0.5 M minus MP. So in such a case, the MP going to mean of the binomial distribution divided by MPQ. If the X is less than MPQ. If the X is greater than MP, then we use the X minus 0.5 minus MP divided by square root of the MPQ. So this is the this is mean and standard deviation of the binomial distribution. So for fixed significance level test, the level the null hypothesis P equal to the P naught. When we reject the null hypothesis, if the Z take the absolute value is greater than the alpha greater than 2, then the one-sided alternative hypotheses are treated similarly. A p-value approach can also be used. So since this is also a t-test, the p-value can calculate based on the t-test. So let me take the example. 1 minute. First, everybody read this example 1 minute. Okay, a foundry produces steel forging used in automobile manufacturing. We wish to test the null hypothesis that the fraction conforming or fallout for this process is 10%. So P equal 10%. So in a random sample 250 forging, 41 found to be non-conforming. That means it is defective. Non-conforming, that means defective. Defective. So what is our conclusion about when the alpha equal to 5% is utilized? So tested, we calculate the test statistics. So going to compute MP X. So in which the X is equal to 41, right? What is the MP now? N is equal to, yeah, let me do. N is 250. Then P known is 0.1 is equal to 25. So equal to the 25, right? So N times P known equal to the 25. However, X is equal to 41. Let me see that. If the X is greater than MP, so going to do the binomial adjustment, X minus 0.5. So X minus 0.5. The minus MP known is equal to 25. Then divide by MPQ. N is 250. The P is 0.1. Q is 0.9. So the Z is obtained 3.27. In this case, alpha equal to 5%. Okay, let me ask again. This is two-sided test or one-sided test. 朱展成
Two-sided.
Two-sided. Thank you. So then, Z, we're going to check the Z.025 is equal to the 1.96. So 3.27. So we're going to reject the null hypothesis, or we do not reject the null hypothesis. Chen Jionghan. Chen Jionghan. Hello? Chen Jionghan. 在吗？ Hello. OK， 假如你不回答，我就旷课咯。陈威成，
老师我在。
说话。So Xenon we compute to be, I'll compute as a 3.27. Then the Z-score we check out from the lookup table is equal to 1.96. So we're going to reject the null hypothesis. We do not reject the null hypothesis.
Reject.
Okay, why? Can you tell me the reason? Why?
Because not equal, the 4i is not equal to 0.1.
Why? based upon what? Based upon what base? What evidence do you base upon to draw this conclusion? 你基于什么样的证据做出这样的决策 ？Why？徐志航，那是念菊吗？徐志航。
对。
Okay. How about you? What is your conclusion? Based on what evidence you draw that conclusion?
Conclusion.
你是怎么做这个决策的？你怎么下这个结论？Why? How?
我不太知道。
Okay, thank you. 洪义凯。Hello? Hello? 洪同学在吗？洪同学在吗 ？Mr. Hong? No. Okay. Miss 董静怡。
因为3.27超过了1.96，在那个 critical region 那边，所以 reject.
All right, thank you. So its reject p-value is also we calculate the p-value is so small, the 0.00 almost equal to the 0.1%. So that process fraction non-conforming or fold out is not equal to 10%. This cannot be true. Cannot be true. Since with our p so p equal to that, so since there 41 out of the 250. Yeah, let me do the calculation. 41 divided by 250. This is about 0.164. 0.164. So that is way, yeah, it's a way greater than, this is a way greater than 0.1. Right, okay. So this is a confidence interval for the population proportion. This is the P, and so once we get a P, then so there are several approaches. Let me introduce the first one. If n is quite large, n is large, P is greater than 0.1, say that the normal approximation binomial can be used like this. We use the Z alpha over 2 minus Z alpha over 2, the PQ divided by N. The P can be estimated by X divided by sample size if N is really large. So if N is small, then the binomial distribution should be used to establish a confidence interval. Yeah, hold on. Let me see that. If the n is small, the binomial distribution should be used to estimate confidence interval on P. So M is large, but P is small. The Poisson approximation to binomial will be useful. So example that two are given by Duncan. That no, actually most of the case we think the M is quite large. N is really, really large. So, okay, then this is example. So if a random sample 80, this is X by an automated decision system, 15 out of the application are not approved. The 15 out of, so this is 0.87, is greater than 0.10. Assuming that no more approximation can be utilized, so alpha equal to the 5%, like this. So on the interval, on the fraction of the non-conforming mortgage application, so we just plug in that, this is 0.8575. And this is the P, this is Q divided by N. This is the P, Q divided by N. And this is the Z, 1 alpha over 2. That is the Z 0.025. Okay. So finally reduce to the 0.1020 and the 0.2730. Yang Ting, could you interpret the confidence interval about the proportion between the 0.10 and the 0.27? Yang Ting.
draw the conclusion 吗？
你行不行解释？我讲中文好了，就是说你怎么去解释这个，信赖区间介于1020跟介于2730。How would you make a conclusion about or interpretation about the confidence interval?
就一开始的那个 P H 是0.1875，所以它是在这个 confidence interval 里面。
All right, let me do the interpretation. Thank you, Yang Ting. Now you can mute your mic. Thank you. 我只讲一遍啊，我用中文只讲一遍啊，我等一下再用英文讲啊。真正的 p value 是不是在0.1020跟0.2730，我们永远不知道。We never know what exactly the location of the p should be. We never know. However, 但是我们利用这种方式建立信赖区间。假如我们建立了100次，第一次介于0.1020，然后0.2730，再一次我们一样抽80个样本，看里面有多少个坏的，再建立一次，利用相同的方法建立这样的信赖区间，建立100次。当我们使用显著水准是5%， alpha 等于5%，我们建立这样的100次的信赖区间，因为我抽样1次就可以建立1个，抽样2次可以建立2个，在这种水准之下，5% 水准之下，这100个信赖区间至少有95个会包含真正的 P。我再讲一遍，用这种方式建立100个信赖区间。信赖区间至少有95个会包含真正的 P， 那这个时候再问你了，那真正 P 在哪里？我们还是不知道。这就是信赖区间的解释，考试一定考。OK, let me do it again. Let me do it again. It won't matter what the real location of P is. We never know, since it is a sampling interpretation. If we follow the sampling plan, we draw the 100 sample and build the 100 confidence interval about P. At least 95 out of 100 will contain the true P, even though we still don't know what is the exactly P is. Okay, that would be the interpretation. 那个陈九汉同学在吗 ？Hello， 陈九汉不在哈。洪义凯在不在？
在。
那刚刚问题目为什么不在了？
我刚才去厕所。
OK。陈总和这个同学班长要不要打个讯息给他，请他上线？
老师，那个陈总和他那个网络电脑连不上，他家里那个数据机要重开一下。
OK， 好。那他现在到底上了没有啊？
我问问看他，看他。
Okay, then we move to the type 2 error and the sample size. So this is beta. Then could you tell me what is a type 2 error? What is the definition of the type 2 error? Zhu Zanchen, would you tell me what is the definition of type 2 error? Zhu Zanchen.
在。
Okay, would you say what is the definition of type 2 error?
就是 null hypothesis， 就是我们接受 null hypothesis， 可是它其实是就是 false 的。
Okay, excellent. Good point. Really good point. So we assume. So this is the null hypothesis. However, this is not true. We still accept the null hypothesis. So when we accept the null hypothesis, the test statistic need to fall within this boundary. Must fall within this. However, the true mean has been shifted to the here. So not is no longer here. So actually, this is the true distribution. Then this between this boundary, we commit the type 2 error. So corresponding to that, do the transformation, do some algebraic calculation equal to the z alpha over 2 minus the delta and the square root and divide by sigma. So the delta equal to the absolute value, actually the mu1 minus mu0. Okay, let me just 1 minute read this example. 1 minute, please. Everybody read this example. Okay. Okay, back to the whiteboard. The mean content of coffee cans filled on a particular production line are being studied. The standards specify that the mean content must be equal to 16 ounce. So that is equal. No hypothesis. And from past experience, it is known that the standard deviation of can content is 0.1 ounce. Sigma is equal to the 0.1 ounce. So this is assumption. So from the hypothesis can be constructed. This is two-sided test, right? Mu9 equals 16. And the random sample of 9 can in here, when we read this statement, we understand n equal to 9. Use the type 1 error probability specified as a 5%. This is our alpha. So therefore, the test statistic can be computed based upon this. X minus 16 divided by 0.1. The standard deviation divided by square root of n. So, and no hypothesis is rejected if the absolute value greater than 1.96 and alpha equal 5%. So we try to find the type 2 error and the power of the test if the null hypothesis, the null hypothesis, and it's not true. If the true mean mu1 is equal to 16.1 ounce. So actually mu equal to 16 is not true. The true is 16.1. So we calculate the delta. As we previously mentioned, the delta right here. The equal to the 0.1. So we have the plug-in all the parameter into equation 4.46 in here. So 1.96.1 square root of 9 equal to 3 divided by delta equal to the 0.1 and minus z minus 96 minus 0.1 times 3 divided by divided by sigma. Sigma is 0.1 as well. We have it. So finally, this is the phi of the minus 1.04 minus phi minus 4.96. The second term is almost close to 0. Since this value is way smaller to the left side, like a normal distribution. So the minus 4 point something, 4.96 is way away from to the 0. So the probability on to its left is so small, it's almost equal to 0. So we found the type 2 error. This is the beta is equal to 0.1496. Then, how about the power? How can we calculate the power? How can we calculate the power? Mr. Bai Tong, would you answer this question?
power 就是把1减掉那个 beta， 就是把1减掉0.1492。
Okay, thank you. Great. 1.1496. 492. That's going to be our power. Power is about 85%. Okay, thank you. So this is called the OC curve. The OC curve. For the two-sided test, when alpha equal to the 5%, and this is reproduce a permission of those guys, the operating characteristic curve. For the common statistical test, significant error of the mathematical statistics is almost 80 years ago. So this is the D. D is the delta. And for different sample sizes and the type 2 error. Then for here, D, in which case? 0.1, yeah, it's way too small. This is like this. Yeah, this is like this. And sample size equal to 9. 9 is around right here. It's almost here. Oh, yeah, there's something like here. So from here, we can check out the bit. No, actually, no. The beta should be in the 1492. Hold on, let me see that. This should be close to 0.1. 129. Okay, this is things that this is very difficult to match up. We really strongly recommend you just directly calculate by yourself. Do not directly look in this this graph. This graph this is only for your reference only. Since you like to n equal to 9, you need to check this is in between 9 here. And also like to check the D. D should be the delta and divide by the sigma. So it is not so convenient to use, just for your reference. Okay, from the mini tab, this is easier, much easier for you to calculate the type 2 error. From this example, the difference, the 0.1 and 9, and we can calculate the power. So the power of the sample size. Then this is for example 4.7 for 4.3. The same. It can be obtained from the mini tab from the power. As long as you know the power, then the type 2 error can be obtained. Okay. Then we move to the statistical inference about the two sample. Once while there's a two population, the sample 1 and the sample 2, we can be considered this is a class J, this is a class E, and then we like to do the comparing mean, comparing variance, comparing proportion. So inference about the difference on mean, the variances known. Once while the sigma 1 square, sigma 2 square unknown. Then we use Z. And also they are independent. So we take the expected value of the difference equal to the mu1 minus mu2. We take the variance equal to take the variance of the x1 bar minus x2 bar. Since that they are independent, so they are sigma 1 squared divided by n1 plus sigma squared divided by n2. So they are assumed they are independent and variances are known. So this is testing procedure. Sigma 1 minus sigma 2 equal to the delta norm. And this is null hypothesis. And the null hypothesis test statistic is x1 bar minus x2 bar minus delta norm. This is a null value. This is a null value. And divide by is our test statistic. So this is the two-sided test. If the alternative hypothesis is not equal to delta norm, in between the critical region, so a set, if it is outside the critical, so no, it is smaller than the lower critical value or greater than the upper critical value, we reject the null hypothesis. And this is how we calculate the p-value. Alternative is a greater than if the test statistic is a greater than the upper value, we reject it. So the p-value must be the upper tail. If the null hypothesis is less than, then if the test statistic computed is smaller than the lower critical score, then we reject the null hypothesis, and p-value is equal to the tail to the left. 1 minute. Please read this example. Okay, back to the whiteboard. A product developer is interested in reducing the drying time of the prime painting. Two formulations of paint are tested. There's two different formulations. Formulation 1 for the standard chemistry. Formulation 2 has a new drying ingredient that should be reduced the drying time. So we assume we like to dry the paint. We have a new recipe. So for experiences, it is known that the standard deviation of drying time is 8 minutes. Just 8 minutes. Go to the 8 minute. And this inherent variability should be unaffected by addition of the new ingredient. So that is to say, sigma 1 squared gotta be equal to the sigma 2 squared equal to a squared. They are equal. So from this statement. So now 10 specimens are painted with Formula 1. So this is the 10 N1 equal to 10. Another 10 specimens are painted with the formulation 2, the N2 equal to 10 as well. So the 20 specimens are painted in random order. The 2 sample average are calculated 121 minutes and 112 respectively. So what is the conclusion can the product developer draw about the effectiveness of the new ingredient about the when alpha equals 5%. So originally this is the original recipe. Now we use the new recipe. The drying time reduced from 121 to the 112. So is this really good enough? So so the null hypothesis are now actually mu1 minus mu2 is equal to 0. That means the drying time are still the same. Or if the 121 is much greater than 112. Yeah, if this is true, then we reject the null hypothesis. That means the new recipe is effective in reducing the time for drying. So we calculate in terms of the Z sampling distribution. Finally, we arrived at 2.52. 2.52 is, since this is a one-sided test, the Z.05 is about the 1.645. So the 2.52 is greater than 1.645. So we reject the null hypothesis. It cannot be true. So that means the drying time has been significantly reduced by this new ingredient added to that chemistry. So concluding that, adding into that the new ingredient to the paint significantly reducing the drying time. Or alternatively, we might compute the p-value. Since this is greater than, then we calculate the greater than 0. So then 2 point. Let me draw the illustration. 2.52 is around here. We like to calculate the right tail probability. So we use a 1 minus the CDF of the 2.52. 2.52. Then 1 minus 5 of the 2.52 is only 0.0059. This is only 0.5%. However, in here, the alpha is equal to 5%. So yeah, so we should reject the null hypothesis. The null hypothesis cannot be true. Therefore, null hypothesis will be rejected at any level is greater than any level. So going to reject it any significance level if the alpha is greater than or equal to the 0.0059. As long as alpha greater than or equal to 0.95, we reject the null hypothesis. Okay, we take a break. Okay, back to the board.有声音吗 ？Hello，
有的。
OK， 谢谢。I think so going to skip that. So for the remaining going to quite similar, all the same. And they equal, so okay, there's only one thing I'd like to mention right here. So yes. But about the difference on the mean of the two normal digits when variance unknown. So case one, if they are equal, however, they are unknown. The sigma 1 squared equals sigma 2 squared equals sigma squared. So we use the Poor estimator of the sigma squared, use the SP. Since this is a total degree of freedom, n1 plus n2 minus 2. The degree of freedom n1 minus 1 times s squared. This is the first portion. And n2 minus 1 over the n1 plus n2 minus 2. This is second portion. There's a weighted Poor sample variance. So if they are known, however, they are equal. So this is 1 over n1 plus 1 over n2. Take this SP out of that. So this is first case. Then I'm going to do that. Okay, if case number 2, they are not equal. So use the S1 squared over N1, S2 squared over N2. And there's an approximation of degree of freedom for the T distribution, like this. Like this. So therefore, if they are not equal, null hypothesis is in terms of the two normal, in the means of the two normal distribution are tested. In the equivariances is set the T known star is used as a test statistic. And at the n1 plus n2 minus 2 is replaced by the nu. This is nu. This is the degree of freedom, DOF. This is degree of freedom for the freedom test. Okay, so the confidence interval for case 1, if they are equal, Poor sample variance. Case 2 not equal, so we use a nu. And here, degree of freedom, they are equal n1 plus n2 minus 2. If not equal, we should use the nu, which is approximation by equation right here, 4.55. Nu is defined by this. Okay, 1 minute. Read this example. Example 4.10. Okay, back to here. An article in the journal Hazardous Waste and the Hazardous Material reported that the results of an analysis of the weight of the calcium in standard cement and the cement dope was lead. So reduced level of calcium would indicate that the hydration mechanism in the cement is blocked, and we allow water to attack various locations in cement structure. So this is like a seeding, we use a cement. The 10 sample of standard cement had an average of the 8%. I'm sorry, the average 8% calcium of X1 equal to the 90.0 with a standard standard deviation equal to the 5.0, and the 15 sample of the lead dope cement had the average weight percent calcium that is 87.0 with a sample standard deviation equal to the S2 equal to the 4.0. Is there any particular evidence to support the claim the doping the cement with the lead changed the mean weight of calcium in the cement? So that is a one dope. The lead changed the mean weight or not? So this is the question. So we will assume the weight percent calcium is normally distributed is a 95% confidence interval. So we assume the sigma 1 square equal to the sigma 2 square. Then the SP should be computed. Therefore, the poor standard deviation estimate is about 4.4, and we calculate the 95% into that. Finally, this is between the minus 0.72 and the 0.672. Does it actually it is really covered zero. So know that 95% counting interval includes zero. Zero is in between. Therefore, at this level, we cannot conclude there's a significant difference in the mean. And put another way, there's no evidence that the doping the cement with lead affected the mean weight percent of the calcium. Therefore, we cannot claim the presence of the lead affected the aspect of the hydration mechanism at a 95% level of significance. So we can, so the null hypothesis cannot be rejected. So this is the mini tab, and this is the t-test, Yeah, let me, this is in here, the alpha equal to 5%, sigma is around the 2.7 is right here, SP. Hold on. This is the catalyst one. Oh, hold on, let me see that. T value, degree of freedom, hold on. T value. No, this is not corresponding to this. This is corresponding to the other example. Okay, this is a different one. Sample size, let me see that. So let me check what is the total sample. This is 25. The N1 plus N2 minus 2. So this 25 should be 23. This is a different. Okay, this is the other example, not corresponding to that. Okay, then pair data. Let me see that. Okay. Then there's another called the pair data. If the the data are dependent, I mean there's a pair data. This we compute the D1, DI equal to the X D1. Let me say that DI DI1 minus XDI2. So there's a two specimen, however, they are dependent each other. So that's called the pair data dependent. Dependent data. The two different types of the machines are used to measure the tensile strength of synthetic fiber. So we wish to determine whether or not the two machine yield the same average tensile strength value. So a specimen of the fiber are random select specimen like this. 1, 2, 3. Totally, we have 8, for example, specimen. Then we test 2. Test 2. For each specimen, told you we have a specimen to test the two different machines. So it's made using each machine in each specimen. So the data in this experiment has been paired to prevent the difference between the fiber specimen, which could be substantially from affecting the test. So you can see that these two data, they are dependent. However, between specimen, they are independent. So in such a case, the pair data need to be compared. So that is the X1 minus X2 is equal to the D1. The second one, X1 minus X2 should be the D2. And this is the D3. This is the D4 until the DN. So in such a case, so the test procedure consists of the obtaining the differences of the pair of the observation on each of the n specimen. So dj equal to the x dj here. This is the equation. dj equal to x1j minus x2j, j from 1 to n. N is the number of specimen. Specimen. So N specimen. Okay, then the difference mu d is equal to 0. So when null hypothesis, we assume since we subtract the dj equal to the x1j minus x2j. So so our null hypothesis is equal to the mu1 equal to the mu2. And this is our null hypothesis. So in the other way, further, the test of mu d is simply equal to the one sample t-test. Since we already do the subtraction, this is equal to the dj. So that is equivalent equal to the delta equal to 0. The delta equal to the mu1 minus mu2. As long as the mu equal delta equal to 0, mu1 going to be equal to the mu2. So we compute the D bar. This is the D. This is the D1 to D8 D bar, and also compute the standard deviation, the sample variance of the D based upon this calculation. Then the T test statistic equal to the D bar minus 0 in because the delta equal to 0 is used to replace equal to mu1 equal to the mu2. So this is the D bar minus 0 divided by ST divided by square root of n. So this is our test statistic. Minus 1.46. Under the null hypothesis, alpha equal to 5%. And our critical value is at 2.365. So we conclude there's no strong evidence to indicate these two machines differ in their mean tensile strength measurement, since in which case p-value is about the p-value is about 0.18. Yeah, it's quite large. We cannot reject the null hypothesis. Okay. I stop here. Is any question? Miss Dong Jingyi, is this okay to you?
暂时还好。
Okay, thank you. The last one. The inference about the variance of the two normal distribution. So if we assume they are equal, then we take this F known, this going to follow the F distribution with the degree, the sampling distribution of F distribution with the 2 degree of freedom n1 minus 1 and n2 minus 1. And its F is also behave like that, so like that. This is upper, this is a lower. And then this is a 1. If it is two-sided, this is a 1 minus 1 alpha over 2. And the lower going to be the alpha over 2. Okay. So this is test statistic. The test equal to that. And the alternative hypothesis is sigma 1 is less than sigma 2. The bigger one put in the numerator. The rejected is greater than that. So this is in the numerator, denominator, the 2, 1. Let me say that 2, 1. Okay. If it is a alternative hypothesis, this is a sigma 1 squared greater than sigma 2 squared. The larger one put in the numerator, smaller one put in the numerator. Larger one put in the numerator, smaller one put in the denominator. This is a 1, 2, and this is a 1, 2. Right, testing. Okay. So this is a confidence interval for the ratio of the two variances of the two, the variance of the two population. And this is upper confidence interval. This is lower confidence interval, in which case only use the alpha. In here, 1 minus alpha, since this is one-sided. In here, we use the alpha over 2. In here, we use a 1 minus alpha 2, since this is a two-sided. Okay. Okay, then I think it should be the last one, the inference about the two proportion. Like here, if we will assume the P1 equal to the P2, P1 equal to the P2. We used to use the Z to do the test statistic. And how about P hat? In here. Since the P is unknown, the P should be replaced by the P hat. The P hat we use totally what is the total number of the sample size? N1 plus N2. What is the defect portion? X1 plus X2. And the P hat just plug in into here. So there's a P hat, this is a P hat. And the testing hypothesis of two population proportion. So this is Z and this, if the two-sided, this is a p-value, is a one-sided, this is a p-value. Like the previous one we mentioned. So this is a confidence interval. Okay. If the P1, P2 possible construct a confidence interval for their differences, typically we use that if the sample size is large and the P is not that small. So these results are normal approximation to the binomial distribution. I think more than two. Oh, this is we're going to analysis of variance. So we're gonna stop here. I think chapter 4 only up to here. Equation 4.64. And all the ANOVA, we're going to skip that. Will not include it in the midterm examination. No, the linear regression will out of our scope as well. I'm gonna skip that. Then let me see that this regression should be in the more advanced courses in the senior level or in the graduate level. So okay, I'll stop here. Okay, so I think I let the class let go a little bit earlier. Then next time we're going to start the chapter 5. I'm going to send the slide into the line group for sharing. Okay, thanks for your understanding. Thanks for your cooperation since I'm not in the quarantine time. And any question for today's class? Is there any question for today's class? 来，同学有没有问题？因为今天比较早下课，我们今天把第4章上完了。
不好意思，老师。
是，请说。
我想问回去刚刚前面的。
OK, sure.
应该是
第几页？
书的话是137，是关于
投影片，你直接讲投影片好不好？
投影片的话，可能要导一下回去。这是有 case 1、case 2。case 1那边是2个变异数不等于，一个是 case 2是2个变异数不等于。
OK, 好。在第几页？
可能你要开一下，我导回去，我看一下那个投影片是第几节，不好意思。
稍等。哇，怎么被我划掉乱七八糟？等一下。
没关系，我看一下。
等一下。
苹果。
等一下哈。7月8号，稍待一下。稍待一下。是。有看到吗？还没有。HR 怎么不见了？等一下啊，这跑不出来。好，看到了哈，等一下。 大概是在这里吧，我猜。等一下啊，是再往后这里吗？对，这里是吧？
你现在这样子还是档案的画面？
哦，真的哦，稍待一下，那我再来重新分享，等一下，稍待一下，为什么没有呢？
就可能不用投影片也可以，就。
好，那你直接讲好了。那好来，
那
直接
我的
讲好了。
问题就是那个 case two 就是两个不等于嘛 ，case one 就是两个是等于的，然后后面刚刚的例子是，假设它们是等于的，那什么时候才会是假设？不能假设它等于，就是什么时候才会用到 case two？
哦 ，case two 它会明显的告诉你，因为之前的那个 example 要告诉我说 case two 就是说我中间加了那个铅呐，加到那个天花板的石棉网，它不会影响它的材质。这种 hint， 这种 intuition 就代表说它的本质不会变，它的变异数是可以假设等于。假如说我是一个旧的 recipe， 一个是新的 recipe， 他说它本质不一样，这就代表说两个变异数应该是不同。
哦，好，就我要看它的 wordings。
对啊，这个他不会告诉你，他就从他的 statement 跟 wording 中间给你提示。
哦，好，谢谢。
好吧，这样可以吗？
谢谢，可以。
OK， 好 ，OK，sure。好，同学到这里还有没有什么疑问 ？Any question？ 好，假如没有的话，因为thanks for your cooperation. I'm not in the normal condition, so I would like to appreciate your time and your understanding, especially this on and off from the online class. I also understand this is very difficult for you guys to log in or log on to the Teams software. Sometimes it is not that user friendly. So I see you next week. Bye bye.
徐老师，
徐老师。